Yep, I am live it seems. I got one more subscriber. That is crazy. It was 17 yesterday and now it is 18. That is just crazy. Yes. And we have come quite long way from where we started. Now we are at single instruction multiple data, SIMD, single instruction multiple data sets. And yesterday we began this and we saw the the different ways that we can refer to data that is stored in vector registers, in neon registers, in ARC, in AArch64 architecture. And the whole register consists of 128 bits, and we can divide it in different ways, either two doubles or in four single precision values or in 16 single bytes, and we can access individual bytes from the register like so. In this way, we can say V and then N. N means the number of the register that we are using, and dot, and 16V represents the way that we want to divide this register, and then in square brackets we can index that space from the least bit to the highest bit in whatever way we want. That is just crazy. And these are just different representations. And today, yep, load and store instructions. Let's go. And these instructions can be used to perform interleaving of data when structured data is loaded or stored. Okay, the data should be properly aligned for best performance. The data should be properly aligned for best performance. These instructions are very useful for common multimedia data types. For example, we actually did this part. You were here. Yeah, but whatever. For example, image is typically stored in arrays of pixels where each pixel is a small data structure, such as the pixel is structure showed in listing 5.6, and each pixel can consist of three individual bytes, three values which take one byte each, and that byte represents these three values represent red, green, and blue for that pixel. It will take three double words or quadruple words to hold an even number of pixels without wasting space, as shown in figure 5.10, 10.2. This is the way data should be loaded using an advanced SIMD load instruction. Many image processing operations work best if color channel is processed separately. The SIMD load and store instructions can be used to split the image data into color channels where each channel is stored in a different register as shown in this. Okay, there are certain instructions through which we can separate different values in a data structure and get those different values in different registers. That is crazy. Other examples of interleaved data include stereo audio, which has two interleaved channels, and surround sound, which may have up to nine interleaved channels. And in all of these cases, most processing operations are simplified when the data is separated into non-interleaved channels. In all of these cases, most processing operations are simplified when the data is separated into non-interleaved channels. Okay, our operations can be simplified if we can get data in this format in non-interleaved channels, where each channel is stored in a different register. Load store instructions using one lane. These instructions are used to load and store structured data across multiple registers. We can load data into multiple registers. That is crazy. Load structured data, LD, and store structured data. They can be used for interleaving or de-interleaving the data as it is loaded or stored, as shown in figure 10.3, where is Yes, we can s- store the data like this or like this using these instructions. Syntax operation, which can be LD or ST, and then N must be either 1, 2, 3, or 4. Okay, and then index, okay, and comma, and the name of the register, it seems list. Yeah, what is list? List specifies the list of registers. There are four list formats. Okay, there are four list formats. Either I can do vt.t, starting from register t till register t, or register in register vt. I want the tth section, or divide this register vt into t storage. That is, t can be a byte, single precision, or double precision, or half precision. Vt dot t, comma, vt plus 1 t. Okay, now here I am specifying two registers. That is also crazy. And vt dot t minus till from this till this. Okay, and from t till t plus 2, or like this, or like this, or I can say from tth register till t plus 3. These the registers must be consecutive. Register 0 is consecutive to register 31. Okay, because they are wrapping around internally. T must be B, H, S, or D. Byte, half word, single precision, double precision. The immediate index specifies which element of each register is to be used. The immediate index specifies which element of each register is to be used. Which element of each register is to be used and must be appropriate for the data size specified by the T. Okay. The same element will be used for all registers. The same element will be used for all registers. Okay. Seems like T will be same for both. Xn is the AArch64 register containing the base address. Here, Xn is the arch mm, general purpose register which contains the base address. XM is the AArch64 register containing an offset. I can provide an offset like that or with an immediate value. If a register or immediate offset is given, then the register XN will be post incremented. XN will be incremented afterwards. Okay. The post increment offset, immediate offset if present, must be 8, 16, 24, 32, 48, or 64, depending on the number of elements transferred and the size specified by capital T. The size specified by capital T. Capital T, yes, capital T does specify the size. Yes, yes. Okay. And that offset has to be compatible with the type, with the storage that individual value takes. Well, let's see, and not just start making theories after just reading theories. LDN. N means, what the heck does N mean? Must be just 1 to 4. Temp, store, okay, description, load one or more data items into a single lane of one or more registers. Put xn into temp and byte size into increase. For v belong register list, do go there, go into the list, okay, and go to the index in that list. The index is provided like that. Go to the index provided in that and put memory address. Put the value in the memory at that address into that registers that specific index, and then increase the temp which contains the variable, and increase is equal to the byte size. Okay, and for, and then if there is an immediate, then increase the xn register. Else, if xm is specified, then increase the xn register by xm. Okay, that is crazy and that makes sense. Temp, I'm doing the same, and instead of putting into the register from the memory, I am putting into the memory from the register and then increasing the temp. The thing is same as I did before, and then also increasing the temp by the size of byte that I have, the size of t, the the proportion of the register that I am using. That will be equal to increment that I am putting at the base address. If immediate is present, then increase post increment the base address, and if rm or xm is specified, then increment post increment the base address, like that. Okay, load 3. What does 3 mean? Yeah, that is the thing, right? What does 3 mean? Wait, yeah, I want to store into v0, v1 and v2 registers and divide them into a byte and use the zeroth byte of that register. Okay, use the zeroth byte of that register. Uh, okay, what will this get me? Yeah, this will get me good. In the zeroth register, I will have the red value for the red pixel. In the first vector register, its first byte will contain blue, and the second V2 register will contain green pixel data. And after the end, the address in the, the base address will be incremented by 3. That is, I will skip this pixel and move on to the next one. And then I will start incrementing by 1. I will start storing data from the first address. Ah, from this address. First, I stored data on this zeroth address, then on first, then second, third, fourth, fifth, till then sixth, and then seventh. Now, load and store multiple structures. These instructions are used to load. Let me actually try to do that. There must be exercises. Which, where are the exercises? Wait, this is a long ass chapter. This is still going, and at the end, I have a bunch of SIMD instructions which take up quite a big space, and then I only have 7 questions. And okay, I guess this part is this exercises. This chapter is mostly about theory. Yeah, that is how it seems. And then I have the devices chapter, which tells me about how I can access devices. There is some crazy thing in there. And then I guess there is running assembly without operating system. That is also crazy. Running without an operating system. All of this is just crazy. This thing is crazy. So it seems like that I will have to practice on my own and not rely on the questions, because there are not much questions. So let me do something. I just read something, so let me go and practice it. this. I will try to get this structure into a register. That was me. Stream is streaming. That is good. That is Rust. Um, CD assembly book chapter 10. Go into the folder and in getting pixels.s. Now here I will have in the data section, I will store the pixels, and these will be stored in bytes. Byte, right? One pixel will be 1 byte. Let me store. The first pixel will have 1, 2, and 3 as it's red, green, and blue, and then the next will have 4, 5, 6, 7. Let's say I am defining 8 pixels. Therefore, let me just do it quickly. 14, 15, 16, 17, 18, 19, 20, 21, 23, 24, 25, 26, 27, 8. How many has it been? 1, 2, 3, 4, 5, 6, 7, 8. Look. Hmm. I started at 1. I should have gone till 27. There seems to be a problem. 1, 2, 4, 5. Oh, I skipped 4 here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 37, and yep, till 24. And then in the dot text section, let me say global main is a global label and align things at spaces 2, and then in the main label I will first of all store the frame pointer and the stack and the linker register onto the stack with an immediate offset of 16, right? After that, let me get the base address, ADRP address for the page of the pixels variable in the 0th register pixels at the rate page, and then I will add to it x0 pixels page offset, right? After adding the offset, what do I want? After adding the offset, what do I want to do? Yes, I got the address. I can start loading actually. LD and then a number. What does that number specify? What does the number specify? Number can be 1, 2, 3, 4, right? Does that mean the amount of registers that I am going to access at the same time? 1, 2, 3, 4. Yep, that is what it means. Here I'm accessing 3 registers at the same time, and that is what I'm typing here. This and what is the correct syntax? This and then a list. Lists can be like that. Let me use v0 dot b comma v1 dot b comma v2 dot b, and index is 0, right? Index list index, and then the base address, in the 0th register, and then give an offset of this p. Let me change the index. Let me do this few times. Replace this with 1, 2, 3, 4, 5, 6, 7, 8. Nope, I don't need 8. 7 is good. Good enough. Good enough. Now, how can I check? Let me just return at this point and load pair 29 and x30. I'm returning at this point because I want to see if this, at least this, works without function, without any error. And return client getting pixels and the output dot out. Okay, there are problems and getting pixels. What is the problem? That should not be up. Okay, the register has to come inside square brackets, it seems. Xn AArch64 register containing. Yes, of course, because I am using the address in that thing. Yes, when specifying address, that is what we do. Yep, 1, 2, 3, 4, 5, 6, 7. Yep, that should work. Let's see. Yep, that does compile. So now I need to find a way so that I can print this. How can I do that? To print a pixel. Okay, I need a format string empty has keys, which will be equal to pixel, and then %d, %d, no, %c, nah, %d is good, %d, %d, yep, and then new line. After getting the data below, I do not need the address for the pixels. I need to get the address of the format string, and then repeatedly call the printf function with the new values. And how do I get the new values? I will get them from these registers and store them onto the stack. Store them onto the stack. Yep. This seems fun. But since I am writing D there, then the printf function will look. Since I'm writing D there, therefore the printf function will look for the printf function will look for single bytes. Let me use the printf function will take 64 bytes, 64 bits to print one value, but my three values take only 24 bits. So I want to fix that. For that, I can maybe print a whole register as hexadecimal. That would be cool. LX, I guess that is the way. LX, LX. Yep, I have three registers and these will be used to print all of them. So I can now print them in a single command. Let me get the address ADRP in the 0th register for format string. First, I will get the page address and then add to the page address the page offset. And then what do I want? I want some space on the stack. For that, I will do subtract from the stack some space, let's say 32. I need only 24, but 32 is the space that I get at a time on the stack has to be a multiple of 16. Now I want to store all of these values onto the stack. For that I will do stp stack no str store the contents of the register v0. It is divided into bytes. No, it is divided into singles, into four singles, right? One single is 32 bits. Now I want to access how many bytes? The whole register is 16 bytes long, and I want to access how many bytes? Eight of them at the time. So that would be double, right? So I want to split the register in two doubles and want to access the first one. Is that correct? Two double. Yes, two double does divide the register in two parts. But the thing is, am I using two doubles? Yep, I'm using two doubles because I'm using 8 bytes. One double is 8 bytes long, right? 8 8 is a 64. Yep, that is correct. Now specify the address where I want to store this, the stack. Now I will store v1. Also divide that into two doubles. Use the first double and store them onto the stack with an offset of 8 from the starting one, from the first register. Now the v3, v2 vector register, and split that into double and access the first one and give an offset of this, and then printf, not like that, branch link to printf like that, and then I will get pop from the stack everything that I put there, and then pop from the stack. After this, move in the 0th register 0 and return with that. That should do it, right? Okay, there are some problems. v0 invalid operation for instruction. I cannot store like that. 23. Maybe the syntax is different to use these registers. How can I store values from the vector registers onto the stack? How do I do that? Q0, Q1, Q2. Storing full 128-bit register. Nope, that is not what I want. I can use D, but I want to use storing specific 64-bit elements from a vector register. If your vector register contains multiple double values like this in C, you want to store one specific element. Example, the first D double from a register. Use this. This stores only the lower first D elements of each register. If you want to store the upper, do this, lining the stack for neon registers. But this is giving me error. Invalid operation for instruction. This is giving me error. I think this is just something very Apple specific. Store incorrect. Correct way to store is do this. That is what I have done. You should use this instead of this. Use this. Why? The error invalid operation for instruction means that a store does not support storing a single 64-bit element like this directly. The store instruction expects a full register like D or full Q0. 128-bit register rather than a sub-element like that. What's happening? This refers to only 64-bit elements inside a 128-bit register, but store does not support addressing a single element this way. D0 refers to 64 bits part of V0, which is what you want. What if I want to store, yes, V1? That is a very good point. If you need to store the upper 64 bits of a register, use fmove to move it to another register first. I move it, fmove, from this to this register, and then I store it. Storing full 128-bit register is also that. Okay, let's try to do that. I can do D0 instead of this, and here D1 instead of that, and here D2. Let's see, that should work. Yep, and get this. So what does this mean? 16, not 16, 16. What does 16 mean? Wait, I should give the pixels in binary, right? 0, B, and 1. 0, B, and not 2, that is just great. So for the first one, I should get 1 and 1011. Let's say 1. A single byte is represented by two registers. So for the first one, I should get, what should I get? I should get, let's see what the heck I'm getting. I'll slash out. I'm getting 1, 6 and a lot of zeros and some number. What changed from the first one? What should change? I changed the number in, red pixels and in blue pixels. I should see the change reflected in blue and red both pixels, but I do not see that. 171411 0E0B FB0805. Oh, I do see some change here, and yeah, I guess they are stored in reverse order. I see 2 in the original and F in this. F because I made them all ones, right? Yep, this one. So if I do, if I do, let's say, okay, so the first pixel goes to the LSB, and that is the order. First pixel goes to the LSB and the last to the MSB. So if I change this to be in binary, not even in binary, if I change this to be 15 and I change this to be 15 and I change this to be 0, I should see F in the first numbers, MSB first place, and 0 in the second numbers, uh, first place, and F in the third numbers first place. Let me first clang and then is F. Why is there 1? And F is here. 1. Let's see. 1. Why is there 1? I made this 0. Okay. Maybe because of this. This should not. Oh. I am storing them in a byte. Yeah, and 1 byte is represented by 2 hexadecimal numbers. So I should see 0 there. But I do not see 0 there. I see 1 instead. Maybe because of the format that they are being stored. Okay, but the thing is that I am able to load and store these. That is good. Now moving on. to the next thingy. What do we have here? Examples. Okay, there's this, now this. These instructions are used to load and store multiple data structures across multiple registers with interleaving data. LDN, LDS, list, list. This does not take an index. Okay, OP must either be LD or ST, and N must either be 1, 2, 3, 4, specifying the amount of registers that we are using. 1, 2, 3, 4 in the maximum, and only one register here in the minimum case. T must either be 16 byte, 8 byte, half, 8 half words. 16 bytes is the whole register. 8 bytes, 8 half words, and all that. Then XN, the address register, and XM, the register which contains the offset. If a register or immediate value is offset, then it will be post incremented. The post incremented immediate offset, if present, must be 816, 24, 348, and all that, depending on the number of elements transferred and the size specified by T. I used 3 as an offset, which is crazy. Post incremented offset, if present, must be this. Well, mine was 3 and it still work. So yeah, let's see. This is the way to write it, that I want to load into 3 registers. Register this, and this, zeroth, first, and second register, and they have been divided into 8 bytes. And the address is in the zeroth register, and add 24 to the base zeroth register address. Why? Because 24 is the amount uh, of data that I loaded here. Load 16 RGB pixel structures into these. Okay, okay. I think I'm getting how this is done. So in my program, if I remove all of this and just do what? 8 bytes, 8 bytes, 8 bytes, 8 bytes, and do this. This should still work, I guess. Oh yeah. Um, that was here. Remove this. Yes, I think this should work. Not clang. I am in the correct folder. Yes, and put the output dot out, dot slash out, and does it still work? So I have replaced using all of those instructions by using only these 2 instructions. How does this work? Let's see. I put the base and address in temp, and increase is equal to size t, and then I will do for x is my own little variable, x from x till n lanes, that is how many different channels, how many different, into how many different mm, number of storages have I divided my main register, that is in this case 8 bytes. So n will x will go up to from 0 till 8 till 7. At 8 it will get out of the loop, and then inside, for every register in the list, which can be 1, 2, 3, for the first register I will get into the, starting from the first is zeroth place, I will store the address and then increase this by that and store the next item at the in the memory into the second register's zeroth index and then into the third register's zeroth index. After storing into each register, I will move on to using the second part of those registers. Okay, and then if there is an offset, I add that, and if whatever is the offset, I add that, and then I end. And here is the same process in reverse for storing. Oh, I can store like that. Okay. Not, yes, and let's see where is my store instruction. Here I am storing it like this, but I can store all of these T3 registers at the same time. How? By saying that I want to use the V0 register and divide it into 8 bytes, and also the V1 register and divide it into 8 bytes, and also use the V2 register, divide it into 8 bytes, and then start storing at the stack. This should also work. Should it? Yep, it should. I should get the same output, which I do not get, unfortunately. I am getting something strange. F13100. Is there any F13100 anywhere? Nope. Nope. Nowhere. Or are these just reversed? F05. Is there any F05? There is a F15, but not F05. Yeah, so I guess getting pixels. This has backfired a little. Oh, now I am getting individual pixels at this point. Yeah. Okay. These are individual pixels, which is not the right way that I want to store them. I want to store them like that. All the red values at one place, all the blue and all the green at one place. Well, there has to be an order to this. I got the red value. This must mean these two must represent, I guess, the red value in one of the pixels. 80. What does 80 mean? 80 means 8 into 16. 8 into 16 is 832. 32 into 4, 128. Is there a 128? Nope, there is not a 128. But we got this. Now, load copies of a structure to all lanes. Load copies of a structure to all lanes. Okay, I specify a structure and then copy that into all lanes. This instruction is used to load multiple copies of a structured data across multiple registers. LDNR load copies of structured data. The data is copied into all lanes. This instruction is useful for initializing vectors for use in later. LDR, list, and then the base address. Okay. N must be one of 1, 2, 3, 4. List specifies the registers starting from any 1 till 4 is the maximum limit. The registers must be consecutive. Register 0 is consecutive to register 31. T must be either 16 byte, 8 bytes, 8 half byte, 4 half word, 4 single or 2 single or 2 double or 1 double maybe. If N is 1, then T can be 1D. XN address. If a register or offset is given, then this. Okay, let's get down to this. LDNR, put xn into a temp, and increase is equal to the size of t, that is into how many, into the size of chunks that we have divided our vector register. For registers, for every register belonging to the list, do for x0 to number of lanes, okay, into number. X will go from 0 till the numbers, till the number of chunks that we have divided an individual register into. And at that position, for every register starting from 0 till the maximum, till the last chunk, starting from the first chunk till the last chunk, I will be putting whatever is in the memory place into that register, the same thing from the memory place into that register. Okay. Hmm. So if I have a pixel 1, 2, 3, then I will get the 0th register filled with ones, and the second register, the first register filled with the register number 1 filled with ones, and register number 2 filled with threes. That makes sense. And then I'll just add the offset. And here is the example. Load 3R, load 3 registers, these 3 with whatever is here, made total 8 copies for everything, and load them. So getting here, if I do R, I should get, I can just remove the remaining ones like that. And what do I expect to see? In the first register, I expect to see 1, 0, 1, 0, 1, 0, 1, 0. And in the secondary register, I expect it to be F, 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 all the way F. No, F0, F0, F0. And in the last register, I expect it to see 3, 0, 3, 0. Let's see. 1, 0, 1, 0, F0, F0, 3, 0, 3, 0. That is correct. So data is being copied. Now, data movement instructions. While the additional register views added by advanced SIMD, there are many more ways to specify data movement. Instructions are provided to move data using the advanced SIMD views, the FP neon views, and the AArch64 integer register views. Okay, the results this results in a large number of possible movement instructions. There are a large number of possible movement instructions. That is a lot of things to keep in mind when you are actually not practicing that much, and you actually do not even need that much. The basics of assembly are like more than enough. And the amount that I know at this point is, I guess, pretty enough for my everyday use assembly. Like I'm going to use assembly. But yeah, this is good. The duplicate instruction copies a scalar into every element of the destination vector. The duplicate instruction copies a scalar into every element of the destination vector. Okay, the scalar can be an advanced SIMD register, okay, or an AArch64 integer register. The instruction is this: duplicate scalar, give a vector register, and this. Okay, I have some value that takes up the all of the 8 bytes of this xn register, and that value will be copied into both the double bytes the of this VD register, TD, tidy, TD2, TD2, wn half td2 td2 td1 td2. This can be sing 4s or 2s, and this, yeah, this makes sense. FD, floating floor float D. TD1 may be 8-bit. TD1 may be 8 bytes. Divide the register into 8 bytes. 16 bytes. 4H, 8H, 2S, or 4S. The lowest n bits of WN will be used when n is the number of bytes specified by TD1. Okay, when n is the number of bytes specified by TD1, then the lowest n bits of WN will be used. TD2 may be, let's see, TD2. This, and this can be anything depending on what is here. TS, TD2 can be 8 byte, 16 byte. Yes, same as this, it seems. And also 2D, because I could be using a, a double value from this register. And then FD may be any FP register, names used in chapter 9. And TD3 may be byte half single D, TD3, T dot TD3. Yep, divide this register into byte half single or double, and get this index of that divided register. The immediate index must be valid for type of vector element specified. The immediate index must be valid. Yeah, that makes sense. Move FD VNTD index as an alias for DUP. Move from this into this is an alias for DUP. Duplicate from this into this. Huh. Because here I am using FD double and VN and TD double. The move FD The movefd fn function, which is also introduced in chapter 9, is an alias for dup this. Okay, dup operations. Duplicate the value in the xn register into the two double bytes that I have divided this vd register into, and here the same for 32 bits, here for any number of bits that I want. Duplicate this into this. So here I am using 32 bits, and in those 32 bits I will copy 8 bits from W1 to 8 8-bit elements. Yes, I will copy 8 bits because here I have divided V0 register into bytes and 8 of them. So I will take the lowest byte from W1 register and put that byte into all of these 8 bytes. Duplicate V2H1. I have divided the V2 register into half, and I'm taking the first half of that V2 register, which is half takes up 2 bytes, and I have divided this V3 register into 8 halves. So I will store those 2 bytes at 8 different locations. Copy 16 bits, which is 2 bytes, halfward from V2 to 8 16-bit elements of V3. Yep. Move vector element. These instructions copy one element into a vector. Move unsigned signed. Copy element into a vector. Copy unsigned element from vector to AArch64 register. From vector to AArch64 register, and copy signed element from vector to AArch64 register. Okay, here move from this to this, from this to this. Here it is said from vector to us. Oh, when I have given a sign or something, then I set the register here, and here is the vector register. Here are the general purpose registers on the left. On the right, I have the vector registers. That is great. Okay, not crazy, but okay, with the index and the way that I have divided their bytes. I can like literally slice this register and pick out individual bytes. Now, T may be 8 bits, 16 bits, 8 bytes, 16 bytes for half word and all of that. The lowest n bits of Wn will be used where n is the number of bits specified by T. The type T2 may be all of these. Yeah, like any of the types available. Type 3 may be byte or half. Why type 3? Because I am, it would be byte or half. Yeah, it would be byte or half because a half takes up 32 bits. Half takes up 16 bits, and I am here using 32 bits. And if I want to store a 32-bit value from a register, from a vector register to a general purpose integer register, I can simply use move. But I do not want to. I'm using this. So this has to be bigger, and this has to be smaller. And 4s, maybe any of these 4s unsigned. I can access any of them. Divide it into as many places as I want. That is crazy. To 2s and 4s, anything. Okay. And 40 maybe byte h and s. My bad. Me feeling sleepy, but me will not sleep. Both immediates, index 1, index and index 2. Yep. Must be valid for the type of vector element is specified. Yep. And INS Vikrant, INS VDT index WN is an alias for move this into this. And oh, I can use INS. I will prefer to use move. Yeah, I will prefer to use move instead. These are the examples. Well, these are the examples. This is how they are performed. They are sign extended or zero extended if I'm using a signed or unsigned number on this and move immediate. What does this do? This moves the value from this to this, and this moves the value from this to this, and unsigned extends the value. Oh, okay. That is pretty bad that I'm trying to sleep and now looking at the time. It has been 1 hour and we have been doing good. These move immediate. Move. I can immediate. I can move an immediate value from one place into the register. These instructions are used to load immediate data into the vector registers. Yes. MI and MVI. Move I and MV and I. Move immediate. Move vector immediate. Vector not vector move not immediate. Vector move not immediate. Float vector floating point immediate. F move. Okay, F move I move into this value, and I can have a, a logical shift. SOP can be logical shift left or logical shift right, I guess, and here will be the shift number for this. And move I can be like this. I can provide an 64-bit immediate value. That is crazy. And yeah, and floating point immediate. I can even provide a floating point immediate if I'm using fmove. Okay, SOAP may be logical shift left, multiple shift left, where MSL is a left shift which fills the lower bits with ones instead of zero. Okay, with ones instead of zeros. MSL shift in binary. What is MSL? Shift in ones maximum length sequence. No, what is OI MSL? This will move this number this by this many bytes, 8 bytes. No, not 8 bytes. Move this by 8 bits. Hmm. This man is doing this in C++. C++ is a crazy language, crazy complicated language, which I will be learning at some point in the some future. Why is this not charging? That was stupid. What is the full form for what is the full form of MSL, right? In binary shifting. MSL does not have any widely recognized full form, however, you might refer to most significant left. This could refer to shifting the most significant bit MSB towards the left. Okay, multiply by shift left, since left shifting in a binary efficiently multiplies the number. So no, this is a AArch64 instruction which 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 shifts left and fills the LSB with ones instead of zeros. Zerex. In AArch64, the instruction you are referring to, MSL, move and shift left. It is commonly used for bit manipulation where a pattern of ones need to be introduced. Shift behavior MSL equivalent to SLL, but filling the LSBs with ones instead of zeros. It is called move and shift left due to some reason which does not specify its exact the thing that it is doing. But still, let's go with it. That is how software engineering is, I guess. The SOP is not present. If SOP is not present, then shift is assumed to be an LSL shift with shift amounting zero. With shift amount of zero, if SOP is this is not present. Yeah. The valid combination of T and shift are given by the following table. Yep. If I have 4 half byte or 8 half byte, shift can be 0 to 8, 0 or 8. Description, replicate logical left shift this to each 16-bit element into each 16-bit elements. Replicate logical shift left. Okay, this is just moving, but I'm not providing any index, so how will this value go there? Will this be multiplied? I don't know, duplicated like in the duplicate instruction. Move immediate for if this is the shift, SOP is this, then I can, and if T is two single or four singles, two singles or two singles means 64 bits, and if that is the case, then the maximum shift that I can achieve is 24. Okay, replicate LSL and it shift into each 32-bit element. Okay, in Arch 64, when doing move immediate V0 and byte, and then I can do byte, right? I can do byte without a doubt. Yep. And then an immediate value. Let's say 100, 132. Will this store this 132, which is a single byte value, into all of the byte divisions of the V0 register, or will it store store 132 only in the lowest byte? Where will it store it? In AArch64 SIMD and floating point neon instruction, the instruction this stores the 132 stores the value 132 into all bytes of V0. So it is kind of equivalent to the double register. That is cool. Unsigned immediate 2064 may be used, maybe or this either this or this, nothing else. Okay, that is a limitation, I guess, but that is fine. TD maybe 2s 4s or 2D. Okay, that also makes sense. I can divide the register in single bytes and have two chunks of single bytes, have four chunks of single bytes, have two chunks of double bytes, have two chunks where each chunk has uh, double bytes. Double bytes, by double bytes, I mean 64 bits. FP floating point immediate may be specified either in decimal notation or in hexadecimal using IEEE standard encoding. Should I have to give the IEEE standard encoding, the value must be expressible as this, wherein the value has to be expressible like this, where n and r are such that n is less than equal to between 16 and 31, and r is between 1 and 3. And this is about the math thing that we saw in chapter number 8, I guess. It is encoded as not a chapter, yeah, chapter 8. It is encoded as normalized binary floating point number with sign 4 bits of fraction and 3-bit exponent. Okay, yep. Again, move immediate or move not immediate. What does this do? Move not immediate. I want to see that. It will find the not after shifting the number, put it into C, and n has hash of number of elements. Okay, number of elements. I will go from I this and keep storing that. Replicate replicate complement of immediate data, possibly shifted into each element. This will add a complemented version of the data that we want to store. Okay. Now with transpose matrix. I have heard transpose matrix, and I am very ashamed that I cannot recall what a transpose matrix is. Advanced SIMD provides two versions of transpose instructions that can be. Transpose is a, I guess, set of operations that we apply to a matrix, and then the resulting matrix is called the transpose of the original matrix. There are two versions of transpose instructions that can be used together for transposing 2 by 2 matrices. Figure 10 shows two examples of this instruction. The instruction is transpose matrix. Yep. And I hope it is charging. Yep, it is charging, but very slowly. Transpose 1 or 2, that is, I'm using one matrix or two matrix, I guess, then a destination and two input matrices. So here, what do I have? TR1. This is my instruction. I'm storing in V13 in this matrix. The result and transposing V14 and V15 matrix. And I have divided them into 8 half words. V13 is the destination. And how many are these blocks? 1, 2, 3, 4, 5, 6, 7, 8. 8. There are 8 of these blocks. 8 of these blocks. What is the base that I'm using? 16. After 16 comes 32. Am I using base 32? And with base 32, I can in with base 32 actually, with 32 bits, not 32 bits. Base 2 means 1 byte, base 4 means 2 bytes. No, yeah. With base 4, a single digit is maximum is 31. And okay, with base 32, I am using 5 bytes, 5 bits. It seems, yeah, 5 bits, 5 bits. It would make sense because base 16 can be represented using 8 bits, using 4 bits. Therefore, base 32 could be represented by using 5 bits. What if I'm using only 2D? Then I will get the last from here and the first from here, 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 here. 31 comes above 30, and V31 is here, V15 is here, this register. So second registers, first element will come here, and first registers, first element will come there in the second place. So here V14 is the first register, 31 is the first, so first registers, first element goes to the second. But that is not what is happening here. Here different things are happening. It is the rules of transpose. So T must be 8 byte, 16 byte, 4 half word, 8 half word, 2 single word, 4 single words, or 2 doubles. Large matrices can be transposed using a division and conquer approach. Divide and conquer approach. Okay. Run one. N is the number of elements, which means this 8 or this 2. So let's say for this thing, n will go from n is equal to 2, and I will go from 0, 0, and then 1, and it will not go to 2 when it does reach 2, and thus this loop will exit. This whole loop, is part of one thing. And then if I is even, then I will, 1, 2, 3, 4, 5, 6, 7, 8, 8. This is even. Then if this is even, I'll get that same location from I goes from 0. Yeah. So this is 7. Yes, this is 7. So I should get here the storage from the 7th register below. If it is even, then I get the main corresponding thing from which register? From register VN. VN is the first register. I will get 0, 1. This is 0. 0 gives me, should give me 0th element, not that one. 2D, 2D. If I is even, that is, let's say, if I start at 0, 0 should give me the first element in the first register. And if it is not 0, then I get, if it is not even, if the index is not even, let's say it is 1. When the index is 1 at this point, I should get 1 minus 1 from the last register. This, and then when I move here, the index is 2, and when it is 2, I get the corresponding element from the first register, and then I move on to 3, and when it is 3, therefore it is E odd, and I get from 3 minus 1 second register's element that is at the second index location. And here I have trn2, that is also crazy. trn2, oh, trn2 has a different algorithm, and here I am using trn2. That is why these two matrices are incompatible. If I is even, then I will do I plus 1. I'll get the value of the next one. Okay. And if it is odd, I will get the exact value. Like in this case, that makes sense now. More sense than before. Get the transpose of this and store it into this. Here, get the second transpose of this and store it into this. Transpose 8 2 by 2 matrices of 16-bit elements. Transpose a 2 by 2 matrix of 32-bit elements in V3 and V4. V3 and V4 is store the transposed matrix in V0 and V1. V3, V4, V3, V4. That is how matrices are transposed, and it takes two registers to store a matrix, it seems. Two single, two single. Yeah, I guess because this is a 2 by 2 matrix, I have four values, and among those, two single byte values are in the V3 register, and two single bytes are in the V4 register, therefore giving me total four elements. And I can even do this for other vectors. Pyeatt shows how the trn instruction can be used to transpose a 3 by 3 matrix. Yeah, right. And then vector permute. These instructions are used to interleave or de-interleave the data from two vectors. To interleave or de-interleave the data from two vectors, okay, or to extract bits from a vector. To extract bits from a vector. Zip vectors, unzip vectors, extract, byte extract. Figure 10.6 gives an example of zip instruction. The unzip instruction performs the inverse operation. This is the way that I can zip the target and destination register and two operands input registers. I can unzip two from two target registers and store it into a single register, or I can extract from these two with an index of this and store it into this figure 10.6 example of zip 1. This zip 2 instruction does the same thing but uses the odd elements of the source register rather than the even elements. So zip 1 takes in the even elements, it seems, and the zip 2 takes in the odd elements. This is to interleave or non-interleave the data. Okay, that makes some sense. Now T is 8 byte, 16 byte. Okay, zip, unzip, all of that. Index, Neelam. Why is there Neelam here? Number of elements. Then I have zip and unzip instructions. I do not know if I will be needing all of this these advanced SIMD instructions. Table lookup, table lookup. So at this point, I have enough understanding about the advanced SIMD instructions. I can convert data from one type to another, and if I ever need, I will not be. I do not imagine myself writing actual code which I will be using in assembly. Right, most of my work will be done in some higher level language, at least languages which are higher level than assembly. So I can actually fast forward this chapter, which I will not be needing, which I do not need at this point, and cannot even imagine where I will be needing, and move on further ahead and finish this book so that I can begin working on something that is more needing, that is more, that takes, that requires more of my attention. That would help me more. Yep. Convert between half, single, and double precision. Okay, I can convert between half, single, and double precision. That is good to know. And then I can print floating point integer. I can f rent floating point to integer, rounding floating point to integer. Okay, that is good. Floating around to integer. Didn't we do this? Round to the nearest zero, negative, plus infinity, minus infinity, and all that thing. Bitwise logical operators. I can do bitwise and or not, uh, or exclusive or BIC binary increase bit clear. Okay, vector bit clear. MBIF vector inverse if insert if false, and BIT insert if true, and BSL vector bitwise select. Okay, these are binary operations which I can perform. Then basic arithmetic instructions. I can add data, add floating point numbers, which I have done in the past. Vector add. How do I vector add? Let me see. Add this, this and store it into this. I can add all the 16 bytes from this register at the same point, from this V6 register to the 16 bytes from 2 of V8 register, and store the whole goddamn thing in the V1 register. And square add. I can square add two vectors of 16-bit signed integers and saturate. Saturate and add. Okay, and I did not use S add because S means signed, right? S can also mean signed, so that is why they have done the people designing assembly. Some people even designed assembly. That is crazy. To SQ add. Okay, now vector add and subtract with narrowing. These instructions add, vector add and narrow, vector add, narrow and round. So this is good to know that I can do all of these things with the processor, telling the processor itself I can add, subtract, and divide by 2. Mind blowing. Cannot even believe my eyes that I can add elements pairwise. That is just too much of a luxury for any human being to have. Or the fact that I can find absolute difference is just mind-boggling. Like, no human should be able to have the feature to find absolute value and negate it. That is just something that gods should have. No human should have the ability to get maximum and minimum elements because that is just something you see in movies and mythical ancient stories, right? Stories passed down from generation to generation. Those characters in those stories, those gods, mythical gods in those stories, are the ones who can count bits. We measly humans, we are not supposed to be doing a scalar saturating operations on bits. We are too dumb to understand the comprehensibility of this thing. To multiply and divide, that is just not something built for humans. And vector multiply and divide, that is not out of the scope of human beings. Multiply and vector by elements. If you see a person who can multiply a vector by element, you can tell yourself that it is a god. It is not any human. Any normal human being cannot be saturating vector multiply and double. That is a god. If some you see someone doing saturating multiply and a double at high level, then you can tell yourself that you are face to face with God. Ask him questions about your misery and everything. Estimate reciprocals. These are mythical ideas, reciprocal step, mythical ideas which are only present in oh, mythology, but not to be uttered by any human being. Multiply scalar by element. Multiply scalar by element. That is just shift in instructions. That is crazy. No human being can shift the unshiftable rock. This can only be done by gods. So God cannot be omnipotent. Human cannot be omnipotent. They cannot create a stone which cannot be shifted and then try to shift that stone. Omnipot Omnipotence self is self paradoxical, is not self possible. What is the term that is used to refer to something that negates its own existence? Uh, Scalar saturation shift right by immediate. Things that negate their own existence, unary arithmetic operators, like the universe, unary. The universe is a crazy place, and we humans have made our vector reduce instructions in this crazy place. This is just imaginary order that we humans believe in. This does not exist, just like human rights. Human rights do not exist. It is just a imaginary order that we have come to believe in and make it stronger by our beliefs over the years. They do not exist in the terms of the universe. They only exist in our collective imaginations, and we are the only ones who do compare. Universe does not care. We are the ones who believe in this imagined order, and when the last human dies, morality dies because Morality only exists as long as we believe in it, and well, morality can die before the last human dies, maybe because the last human stops believing in it, therefore it dies. Morality dies before the human dies. Advanced SIMD intrinsics. The C and C compiler may provide C and C++ programs direct access to the advanced SIMD instructions through the advanced SIMD intrinsic library. The intrinsics are a large set of functions that are built into the compiler. Okay, most of the intrinsics functions map to one advanced SIMD instruction. Okay, there are additional functions provided for typecasting, reinterpreting SIMD vectors so that the C compiler does not complain about mismatched types. It is usually shorter and more efficient to write the SMD code directly as assembly functions and link them to the C code. However, only those who know assembly are capable of doing that. Gods. And then we have exercises, and we can move on to the devices chapter. And at this point, we are pretty close to the end, I would say. What is the time? Not the end of the stream, but end of this book itself. We are at page number 405, and how long is it? The remaining things? How long are the remaining things? We are at devices. Then we have running without operating system, which is also cool. Devices. My goal with this chapter is to get a little bit understanding about how devices are accessed. Just that, how devices are accessed. That's it. That is what I want to know. And then we have running without an operating system, which is all of this, and all of that. Just quite a bit of code running without an operating system. And these things I will never, I don't know, I would, if I would ever be needing these things in everyday life. So my goal with these last two chapters is to just skim through them because I have done the first two chapters, or not the first two, but the majority of the starting chapters with a pretty good way, and I have a pretty solid understanding of basic assembly language. That is good, quite far than I expected myself to come. Now, devices, chapter number 11, and let me just take a sip of water, or maybe a mouthful. As mentioned in chapter 1, a computer system consists of three main parts: the CPU, memory, and devices. The typical computer system has many devices of various types for performing certain functions. Yes, some devices, such as data caches, are closely coupled to the CPU and are typically controlled by executing special CPU instructions that can only be accessed in assembly language. Okay, however, most of the devices on a typical system are accessed and controlled through the system data bus. There is a bus inside the processor which contain which is used to transfer data. Therefore, data bus. These devices appear to the programmer to be ordinary memory locations. These devices appear to the programmer to be ordinary memory locations. Okay, that is cool. The hardware in the system bus decodes the address coming from the CPU. The hardware in the system bus decodes the address coming from the CPU. Okay, and some addresses correspond to devices rather than memory. Okay, okay, that is interesting. Figure 11.1 shows the memory layout for a typical system. Uh, okay, this is the memory layout. Typical hardware address mapping for memory and devices. What is this? This is my main memory, and devices also have some address specified to them. And inside those devices, I can access registers, it seems. Shows the memory layout for a typical system. The exact locations of devices and memory are chosen by the system hardware designers from the programmer's standpoint. Writing data to certain memory addresses results in the data being transferred to a device rather than being stored in memory. The programmer must read documentation on the hardware design to determine exactly where the devices are located in memory. Okay, where the devices are located in memory. So I have an address system with which I can specify memory locations, and that address, the same address system, can be used to access memory, that is RAM itself, and also access devices. And these devices for the programmer will appear as if they were memory locations, and getting data from them will be equivalent to getting input from a device, and storing data to them will be equivalent to giving an output from a device like a monitor screen. Okay, there are devices that allow data to be read or written from external sources, devices that can measure time, devices for moving data from one location in memory to another, devices for modifying the address of memory regions, and devices for even esoteric purposes. Some devices are capable of sending signals to the CPU to indicate that they need attention, while others simply wait for the CPU to check on their status. Okay, that makes sense. When I press a key on my keyboard, I guess, tells my CPU that something is happening. So keep that in mind. And then a modern computer system such as Raspberry Pi, that is a very modern computer system, has dozens or even hundreds of devices in a Raspberry Pi. That is crazy. Programmers write device driver software for each device. A device driver produces a few standard function calls for each device so that it can be used easily. So in a way, it creates an object which has an interface, and that interface can be used to access that device. And that object is called the driver for that device. Driver, which drives the device. The specific set of function calls depends on the type of device and the design of the operating system. Operating system designers strive to define a small set of device types and define a standard software interface for each type in order to make devices interchangeable. That makes sense. And define a standard software interface. Operating system designers strive to define a small set of device types. Operating system designers strive to define a small set of device types. And if your device falls in a certain type, then there are standard software interfaces. And you have to make your drivers which adheres to that standard interface so that that device can be accessed by the computer, because the computer expects to have that interface. Accessing devices directly under Linux, like under the laptop. Devices are typically controlled by writing specific values to the device's internal device. Devices are typically controlled by writing specific values to the device's internal device registers. A device has internal registers. Okay, pen paper for the AArch64 processor. Access to most device registers is accomplished using the load and store instructions. Normal load and store instructions, each device is assigned a base address in memory. This address corresponds with the first register inside the device. The device may also have other registers that are accessible at some predefined offset address from the base address. Some registers are read only, some are write only, and some are read and write. To use the device, the programmer must read from or write appropriate data to the correct device registers. For every device, there is a programmer's model and documentation explaining what each register is in the device does. Some devices are well designed, easy to use, and well documented. Some are not. The programmer must work hard to write software to use them. The Raspberry Pi 3 and some versions of Raspberry Pi 2. For how much can I get the Raspberry Pi? But let's read this first. Use the Broadcom BCM. BCM means Broadcom 2837. 2837. 37. 37. Veritasium's 37 video. System on chip. The single chip contains the CPU and several other devices. The chip contains devices to form a complete computer system on a chip. The Raspberry Pi 3B Plus uses the Broadcom this which provides 5G wireless internet and few other advanced features, but also contains all of the base hardware in the original one. On all of these Raspberry Pi models, the devices are mapped to a memory region beginning at hardware address this and this. Okay, what is Broadcom? This and Raspberry Pi 3, 3,000, 3,000, 2,000 rupees. That is. Oh, isn't this the one whose picture is there in the book? Hmm, I would say they are pretty similar. Yep, here. This is a Raspberry Pi. Oh, yes. Moving back, moving forward. That is life. Now this. Linux is a powerful, or maybe before that. What is this in Raspberry Pi? Pi. PI. Right? PI. Yeah. It looks like you meant Raspberry Pi instead of a Raspberry Pi. The Broadcom, this is the system on chip used in Raspberry Pi 3 models. CPU, quad core, I have 4 cores, ARM Cortex architecture, quad cores, and each core is based on the ARM Cortex architecture, which not only gives the instruction set architecture of ARM, but also they use they use the design provided by ARM Cortex. Okay, and this is the clock speed. Raspberry Pi 3 model this, and this is the clock speed for this one, which is a bit higher. Then GPU, Videocon, RAM. This architecture is manufactured by Broadcom. It is an improved version of this. And I guess I will go to washroom for a minute and just come back in a minute. me back and me drink more water. Yes, we were looking at what the heck is Raspberry Pi and other stuff. System on chip. So now I want to know this. They are saying that this is manufactured by Broadcom. I thought that Raspberry Pi is a company's name which manufactures these, but does not. So is it outsourcing its main product, Raspberry Pi, company? Let's see, no, Raspberry Pi is not a company. It is a brand. It is a brand of single board computers. SBC is developed by the Raspberry Pi Foundation, a UK-based non-profit organization. Okay, who makes Raspberry Pi? Raspberry Pi Foundation, a non-profit that started the Raspberry Pi product in 2012 to promote computing education, focuses on educational initiatives, research, and community outreach. Raspberry Pi Limited company are commercial arm, okay, for-profit company spun off from the foundation, handles the manufacturing, sales, and distribution of Raspberry Pi computers, ensures that Raspberry Pi boards are available for worldwide for hobbyists, industries, and educational institutions. Is Raspberry Pi open source? The software Raspberry Pi, OS firmware, etc., is mostly open source. The hardware is not fully open source as Broadcom owns the chip design. Will you like, okay? So Raspberry Pi is a product which is uh, uh, whose which is sold by the Ras Raspberry, not Raspberry, Raspberry, Raspberry Pi Ltd, and it uh, uses the design by Broadcom and also um, makes Broadcom manufacture, but how do you put it in more legal term? And also outsources the manufacturing to Broadcom. Outsources the manufacturing to Broadcom. Broadcom. Okay. Uh, yeah, that is it. You are mostly right, but let's refine a bit. Raspberry Pi is a product line of single product computers. It is designed and sold by Raspberry Pi Limited, the commercial arm. The commercial arm, as in not advanced risk machines, but arm like hand arm of the Raspberry Pi Foundation. Broadcom supplies the SoC system on chip used in Raspberry Pi boards, such as the this in the Raspberry Pi 3. Manufacturing is outsourced to third-party companies like Sony UK Technology and Element 14. Previously, Premier Farnell, not Broadcom. So Broadcom only makes the main processor, but the whole Raspberry Pi board is assembled and manufactured by other companies like Sony UK Technology Center or Element 14. Broadcom's role is mainly on the chip design and supply, with the actual assembly of Raspberry Pi boards is handled by manufacturing partners. That makes more sense. Linux is a powerful multi-user multitasking operating system. The Linux kernel manages all of the devices and protects them from direct access by the user programs. The Linux kernel manages all of the devices. The Linux kernel manages all of the devices by user program User programs are intended to access devices by making system calls. User programs are intended to access devices by making system calls. Okay, that makes sense. I cannot directly read and write to a device. I have to make a system call and tell the kernel that I want to do something. User programs are intended to access devices by making system calls. The kernel access accesses the devices on the behalf of the user programs, ensuring that an errant user program cannot misuse the device and other resources on the system. Attempting to directly access the register in any device will result in an exception. The kernel will take over and kill the offending process. It will kill you. It will come after you. Linus Torvald, the man, will kill you. However, our programs will need direct access to the device registers. Yes, Linus, Linux, not Linus, Linux allows user programs to gain direct access through the mmap system call. Listing 11.1 shows how four devices can be mapped into the memory space of a user program on a Raspberry Pi. In most cases, the user program will need administrator privileges in order to perform the mapping. The operating system does not usually give permission for ordinary users to access devices directly. However, Linux does provide the ability to change permission on dev mem or for user programs to run with elevated privileges. Okay. Accessing a device does need administrative privileges, and this can be done by changing the permissions in this file, or some user programs can be run in administrative mode for some point. So this is the way to make a system call. These are this is global. This is global. Everything is goddamn global here. In the read only section, I'm storing all this, and in the text here, this is my main function. Where am I making the system call? SVC. Where is the actual system call? Shit. Where is SVC? Close loop. Sub. Oh, so. System call. System call. Okay, of course, I'm not going to read all of this, but I get the idea that this program makes a system call to access some of the device. I'm looking for the system call. For the system call instruction, which actually makes the system call. Address ADR, LDR, ADR, 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 LDR, compare. Branch is not greater than the store move load. Branch link, branch compare, address branch. Branch link, close file. Init close. Branch, shit, so many branches. Branch to close. Okay, I'm not actually making system calls here. It seems like I am calling other functions which do make system calls. Okay, instead of making the system calls myself, like this program by itself, it is calling other functions which make the system call for it. Like we call printf to make the system call for us. One type of device commonly found on embedded systems is the general purpose I/O GPIO device. Although there are many variations on this device provided by different manufacturers, they all provide similar capabilities. The device provides some set of input or output bits that allows signals to be transferred to or from the outside world. The device provides some set of input and output bits that allow signals to be lost, lock in. Although there are many variations on this device, let's see. The device provides some set of input or output bits that allow signals to be transferred to or from the outside world. What the heck does that mean? Each bit of input or output in a GPIO device is generally referred to as a pin, like pins in a USB or in a monitor, which are connected to the computer. Am I in the middle? Yep. Each bit of input or output in a GPIO device is generally referred to as a pin, and a group of pins is referred to as a GPIO port. Ports commonly support 8, 16, or 32 bits of input and/or output, although other sizes are also found in some operating systems. Some GPIO devices support multiple ports, and some have multiple GPIO devices. General processor input output, general purpose input output. A system with a GPIO device usually has some type of connector or wire that allow external input or outputs to be connected to the GPIO device. A system with a GPIO device. We can connect a system with a GPIO device to the GPIO device. For example, the IBM PC has a type of GPIO device that was originally not intended, no allow users, which was originally intended no to allow users to connect a parallel printer. In that platform, the GPIO device is commonly referred to as the parallel printer port. Some GPIO devices, such as the one, what the heck are GPIO devices? What are GPIO devices? Are they just any device like a mouse and monitor which has a predefined interface uh, which has a predefined interface through which has a predefined interface through which in the operating system can access the device. What the heck is a GPIO? What are GPIO? GPIO devices are electronic components that interface with a computer or microcontroller through its GPIO pins. What the heck does that mean? These devices do not follow a predefined protocols like USB, HDMI, or Bluetooth. Instead, they require manual control by the software, making them more flexible but also requiring more programming effort. Interface GPIO pins for a standard peripheral. This protocol custom. These are some protocol bit banging predefined HID for mouse, HDMI. Okay, operating system support, no direct OS support required. Program OS has built-in drivers. Example: LEDs, buttons, sensors, temperature, motions, keyboard, mouse, standard protocols, direct pin control. What do they mean by pin? LEDs can be turned on or off by setting a GPIO pin high or low. Push buttons can send input when pressed and change a pin state. Pin state. Okay, I guess so. These GPIO devices have a set of binary values that that is they have a sort of not a sort of a register, one or multiple, which stores bits and changes to those bits, and the operating system can read and write to those registers, and changes to these bits reflect the state of the device, like an up ls up bit, like an one, like a one in the LSB of a LED light might mean might mean it lights up, and for the programmer to know which bit patterns correspond to which behavior, they can read the documentation for that GPIO, general purpose input output device, and and these bits are also called pins. Is that correct? Yes, you have got the right idea. Let's break it down more precisely. And my mouse has stopped working. The protocol, HID protocol, right? Yeah, what is HID protocol? Um, shit, haunted house API. Mouse HID protocol full form in Hindi. Shit, human interface device. Human interface device. Okay. How GPU devices work internally. GPIO registers. Each GPIO pin is controlled by specific registers in memory. These registers store bit values that determine whether a pin is input, output, high or low. Okay, these registers, a set of bits which can be in mode, a combination of more than one bits determine the state of a single pin. Therefore, a single pin can be in more than two states. The operating system firmware can read write to these registers to control monitors, mapping GPIO pins to registers. GPIO register typically has one bit per pin. Example, bit 0 controls GPIO 0 pin and bit 1 controls this. Example, if GPIO 5's bit in a register is set to 1, the GPIO might output 3.3 high voltage turning an LED. Okay, behavior depends on the device. For an LED, a 1 might turn it on, a 0 might turn it off. For a button, reading a 1 might mean it is pressed and 0 might mean it is not. For more complex devices like I2C sensors, multiple bits might represent a data packet instead of just high low. a data packet. Example, controlling an LED on Raspberry Pi. Let's say GPIO18 controls an LED. Here's how. Here's a low level way to turn it on. This is either define this macro and define this GPIO set equals this set GPIO18 turn LED on, left shifting by 18 bits, sets bit 18 bit 18 in the register which correspond to GPIO 18. Okay, I'm just storing a value in two registers. Are pins and bit the same? Pins are physical metal contacts on a microcontroller or chip. Bit in a register represent the state of those pins. So a pin can either be on or off. A pin can be connected to external devices like LEDs. Pins can be divided. A pin can be connected to two external devices like LEDs, buttons, sensors, etc. How programmers know what bits to use. Data sheets and documentation specify which registers control which bits. Example, this GPIO documentation explains the mandatory addresses and bit patterns needed to interact with the GPIO. Okay, so GPIO is a device which is embedded on a system and it has external physical pins which can be either in on or off state, and these states are determined by the register values uh, uh, in and then other external devices like a LED light can be attached to that external to that GP, GPIO's pin, and changing a specific bit in the GPIO register will that makes a pin in the GPIO send voltage across it will light up the LED. And now for more complicated devices like a sensor, the GP, there are other GPIO pins which can output or input streams of ones and zeros. That is, these special these pins, these other pins can be used to read and write data to more more complicated devices and to more complicated devices. Okay, and the bit patterns which correspond the bit patterns which correspond to the states of the pins are defined by the hardware of the hardware of the computer system, are defined by the GPIO hardware that is on the computer system and not by the external device which is added on top of that GPIO. Is that correct? Yes, you have understood the core concept very well. Let's refine your understanding with a few more details and clarifications. Yes, I am in the middle of the screen. That is also cool. And the stream has not stuck. Yep, not stuck. GPIO as an embedded device with external pins. GPIO is a part of the system hardware, like in Raspberry Pi or a microcontroller. What is a microcontroller? But before that, we are here. It has external physical pins that can be set to a high or low based on register values. Yes, external devices, LED screens, etc., can be connected to those GPIO pins, allowing the system to control or read from them. Simple example, controlling an LED. When you set a specific bit in the GPIO register, the corresponding GPIO pin outputs voltage. Example this on a Raspberry Pi. If an LED is connected to that pin, it lights up when the pin is set high. Okay, and now my mouse is not working. Goddamn GPIO pins. Well, mouse does not work on GPIO pins. It works on a standard protocol. When the pin is low, the LED turns off. More complex GPIO operations communicating with sensors. Some GPIO pins can act as data lines rather than just high-low switches. These pins can send or receive streams of ones and zeros binary data. This allows communication with more complex devices like temperature sensor, motion detectors, or displays. Communication protocols using GPIO pins, SPI, serial peripheral interface, transfers multiple bits at a time fast, multiple bits at a time. Parallel. Okay, like we have multiple lines in an address bus. I squared to IIC. Inter-integrated circuit uses fewer pins but is slower. Well, uses fewer pins and is slower than the SPI. UART, Universal Asynchronous Receiver Transmitter, used for serial communication with external devices like GPS modules and Wi-Fi chips. Okay, okay. In these protocols, specific GPIO pins are assigned different roles. Pins are assigned different roles. Example, clock data chip selection to enable communication with external devices. Okay, who defines the bit patterns? The GPIO hardware itself inside the Raspberry Pi protocol or microcontroller defines how registers control the statements. The external devices example LED does not define GPIO behavior. It simply responds to the signal incoming from the GPIO pins. However, external devices may have their own communication requirements which you need to follow when sending data through GPIO. Okay, so there is this format which is a this is so this is one method to connect to external devices in general ways by using pins, but for more standard devices like monitors and mouse, monitors and mouse, monitors, keyboards and mouse. A more standard approach can be taken, and thus we can make a device specific protocols which have their own faster implementation. Maybe it makes sense. Yes, you got it perfectly. Let's summarize your point and expand on why we have GPUs and standard device protocols. GPIO, a general but low-level way to communicate to connect devices. GPIO provides a flexible way, yes, flexible way to connect external devices by controlling pins manually. Pros: works with custom simple devices, LED buttons, sensors, motors. Yeah, motors. Yes, shit, I can use a GPIO which is embedded on a Raspberry Pi to control a motor, and that motor can be connected with a string which is wound around my doorknob, and whenever I click something, then that GPIO will signal the motor to turn on, and that motor will rotate the knob for some specific time. I can find that out, and thus I have created a automatic door locking or unlocking mechanism, can be used for any digital signal, making it highly versatile. Requires manual control. Example, writing, reading bit directly can be slow for complex data transmission. Example, sending high resolution video. Shit, sending high resolution video using chips, using pins is crazy. Not standardized. Each external device might need custom code to interpret signals. Might need custom code to interpret signals. Standard device protocols, faster and more optimized. For common peripherals like monitor, keyboards, and mice, we use specific communication protocols that are faster, more reliable, plug and play. Keyboard, mouse, monitor, hard device protocol, USB, HIMD, human interface device. How it works: uses a predefined protocol where each key press movement has a known digital representation. Monitor, HIMD, and DisplayPort or VGA transmits video signals in a structured way with pixel timing, resolution, and refresh rates. Hard devices, hard drives, SATA, NVMe, USB, mass storage, optimized for high-speed data transfer with error checking and Wi-Fi, Bluetooth. This and these are protocols. Wi-Fi, this is a protocol, and Bluetooth is also a protocol. Uses radio signals with advanced networking protocols. Why standard protocols are faster is standard protocols are dedicated hardware controllers. Example, USB, HDMI, GPIO on the other hand, it relies on bit-by-bit control, making it slower for high-speed applications. For example, sending video over GPIO pins would be too slow and inefficient. HDMI is optimized with the high-speed clock signals and data lanes to handle millions of pixels per second. GPIO is great for custom low-level control, LED sensors, etc. Standard protocols are optimized for specific devices, making them faster and easier to use. Both methods coexist because some devices, I don't think Mac has a GPIO, and does Apple Mac has a GPIO? I don't think so. Nope, Apple Mac computers do not have a GPIO pins, but built into them, like a Raspberry Pi or microcontroller, do not have built into them like a Raspberry Pi or microcontroller. However, there are alternative ways to achieve similar functionalities. Why don't Macs have GPIO? Macs are designed for consumer product, not for embedded electronics. If that makes sense. GPIO is mostly used in microcontrollers for development, boards for hardware prototyping, and I am in the middle. Oh, gotta go to a little right. Now fine. Yep. Alternative GPIO. If you external USB to GPIO adapter and Raspberry Pi connected to Mac. Okay. Now this typical GPIO device. Each bit of input or output in a GPIO device is generally referred to as a pin, and a group of pins is referred to as a GPIO port. Now it makes much more sense than it was making 15 minutes ago. Ports commonly support 8, 16, or 32 bits of input and or output, although both sizes are also found in some systems. Some GPI devices, such as the one in the IBM PC, are arranged as set of pins that can be switched as a group to either input or output. In many modern GPIO devices, each pin can be set up independently to read for input or drive for output, and different input and output voltages. On some devices, the amount of drive current available can be configured. That is also crazy. Some GPIO devices include the ability to configure built-in pull-up and or pull-down resistors. On most older GPIO devices, the input and output voltages are typically limited to the supply voltage of the GPIO device, and the device may be damaged by greater voltages. Newer GPIO devices generally can tolerate 5 volts on input and regardless of the supply voltage of the device. That is crazy. GPIO devices are very common in systems that are intended to be used for embedded applications. For example, GPIO devices. Individual pins or groups of pins can be configured. For most GPIO devices, individual pins or groups of pins can be configured. Pins can be configured to be input or output. Pins can be disabled so that they are neither input nor output. Uh, input like what is it called? Three state buffer, input, output, or nothing. Like three state buffer, 1, 0, or connection is off. Input values can be read by the CPU, typically high or low. Output values can be read or written to by the CPU, and input pins can be configured to generate interrupt requests. GPIO pins being used as an input and read the state of push button. This is the push button. This is the push button. If this is pressed, this turns to 1. If this is pressed, this turns to 1. If it is off, this is off. Output depends on this. Some GPIO devices may also have more advanced features, such as the ability to use direct memory access DMA to send data without requiring the CPU to move each byte or word. That makes more sense. That makes more sense. I can program the GPIO to save data directly in the memory instead of first getting the data here on the processor and then putting that data in the memory. These are called direct memory access. Figure 11.2 shows two common ways to use GPIO pins. Hmm. Figure 11.2a shows a GPIO pin that has been configured for input and connected to a push button switch. When the switch is open, the pull-up resistor pulls the voltage on the pin to a high state. Pulls the voltage on the pin to a high state. When the switch is closed, the pin is pulled to a low state and some current flows through the pull-up resistor to ground. From this to this. Typically, the pull-up resistor would be around 10k ohm, 10 kilo ohm. The specific value is not critical, but it must be high enough to limit the current to a small amount when the switch is closed. When the switch is closed, current can go from here till here, so that only small current goes, very small amount of current goes, so that current is not wasted in ground. I don't know, that is my theory. Figure 11.2b 11.2b shows GPIO pin that is configured as an output and being used to drive an LED. When a 1 is output on the file, it as at the same voltage as VCC and no current flows. The LED is off. When a 0 is output on the pin, the current is drawn from the resistor and the LED and through the pin to the ground. Through the pin to the ground. This causes the LED to be illuminated. Selection of the resistor is not critical, but it must be small enough to light the LED without allowing enough current to destroy either LED or the GPIO circuitry. This is typically around 1k ohm. Note that in general, GPIO pins can sink more current than they can source. So they can sink more current than they can source. Yes. Okay. More common to connect LEDs and the other devices in the ratio. That makes sense. Right? GPIO seems like one of the good things that I have studied today. GPIO devices. And what is the time? It is coming to an end. And what can we do? I'm going to end in a minute or so. And before that, what can I show you guys? You can look at Raspberry Pi GPIO. Raspberry Pi has its own GPIO and setting the GPIO pin function. Okay, these, god damn it, fuck. These are some offsets which correspond to some pins. These are used to put pins. This offset from the base GPIO address will put an enable clock pin to 0 and this will put it to 1, setting GPIO output pins. We can set output pins and everything. That is crazy. Load the address this and equal to here means this is a literal value, that is it will be stored in the text section, not in the instruction section, but in the not this value will not be stored in the instruction. This will be stored in the text section where no uh, this will be stored at a memory location with an offset from the program counter, and that offset will be stored in here. And when the instruction is being executed, that offset will be used to fetch this value and it will be inserted here instead of this. Cool. And let's end today's stream. That was it. 2.5 hours.